Okay, it's officially recording now.
Yeah, I know.
So, on Tuesday, we had started talking about forces and mass and Newton's second law, F net equals ma. And I showed you, I think, one example of F net equals ma, maybe a second example. But one of our biggest issues with this formula is that we have to figure out all of the forces that are affecting our mass. So our object is in there as the mass, that's its identity. What we do to the object is the acceleration, but the way we accomplish that is by exerting a bunch of forces and then totaling them up. And if we're going to do this correctly, we have to have a way of getting these forces listed without missing any of them. So I have developed kind of a checklist for doing Newton's second law to make sure that I actually get all the forces that are included. First of all, I split them into two categories. And the two categories are distance forces and contact forces. And that may seem like a silly distinction to make, but contact forces are usually exerted by something within our vision of what we can see while we're doing our analysis, whereas distance forces we have to deliberately think about. So let's get that one out of the way first. The big one is gravity. And we'll have two different versions of gravity that we can apply depending on whether we're on Earth's surface or out in outer space somewhere. For now, we're just going to have gravity on Earth's surface. And it might be easy to forget gravity, so that's why I want to take care of it first. Put that on the object if it's relevant for what we're doing. And then we might have electromagnetic forces. Now, we will not have electromagnetic forces in Physics 1. We'll deal with them in Physics 2 if you take Physics 2. But I feel like I'm making a list, so I want to make a complete list, even if it contains a few things I don't need right now. So then we get to contact forces. And like I said, contact forces usually involve something that you can envision when you think about your object, or you can actually see if you make a sketch of the entire scenario around your object. And one type of contact we have is when our mass, the one that's the m in F equals ma, is touching some other object, some other solid object. That's like if I'm doing an analysis of myself and I think about the fact that I'm touching the floor. Maybe I'm touching the wall. Maybe I'm touching a table. And usually, for contact with a solid object, we split it into two parts. One is the normal force that we talked about on Tuesday. This word normal here means perpendicular. So whenever two solid objects touch, there is a surface of contact. The normal force is perpendicular to that surface. So when my feet touch the floor, I receive a vertical force from the floor. When my hand touches the wall, I receive a force that is perpendicular to the wall, which is horizontal from the wall. And when we do inclined situations, then the normal force will tilt over with the angle of the incline. And then there's also the good possibility of a friction force. Instead of being perpendicular to a surface, a friction force acts along a surface, tangent to the surface, dragging against the surface. And these two will usually come together because, as we'll find, it's tough to have a friction force without a normal force. Our basic model of friction that we're going to study next week will link these two together to some extent. So that's your basic idea of a pushing force and a dragging force. We also have the possibility of pulling forces. So we can have tension is the way we usually think about a pulling force. In a sense, the tension force is a little more flexible because it can be in any direction. But usually you get to see what the string looks like or what the rope looks like. So you have a pretty good idea of what direction the force is going to be, because ropes can only pull on things. You can't push on a rope. A rope isn't going to exert a sideways force unless the actual rope is pointing sideways. So for a tension force, we basically know the direction of the force just by looking at things. Now you can have kind of combinations of these things. I could be glued or taped or bolted to the floor, and that would be like a combination of a normal force and a tension force. So an adhesion force or an attachment force could pull or push depending on what you're asking it to do. So it is possible to have both kinds of contact in the same scenario. And then the other big one is the possibility of fluid forces. We're not going to do too much with fluid forces this semester, but I want you to realize they exist. There is a force of static pressure. And this is the force that allows airplanes to fly. There is more pressure on the bottom of the wing of an airplane than there is on the top. So there's more upward force than downward force, and that provides the lift to allow planes to fly. And the reasons for that pressure difference are various and more complicated than we want to get into. There's also the possibility of a drag force or a resistance force. So you can feel this force against your hand. If you stick your hand out the window of a moving car, you can feel the wind pushing your hand backwards. Now, that being said, I do not recommend sticking your hand out the window of a moving car. I have to say this. One time, I was driving down the highway, and my wife had put her hands out the sunroof. And it's a lot of fun, but a bee hit her right in the palm of the hand. And she's allergic to bees, apparently. Now, the stinger didn't get her, but the bee's leg was embedded in her hand. So we had to pull that out and apply ice, and everything was okay. But you can imagine how that could be worse. So don't put your hand out the window of a moving car. And if you do and you get hurt, don't say your physics professor told you you could do it, because I told you not to. All right. So what, this is Tuesday, Thursday. How far did we get? We got to there. Okay. So let's take a look at a situation where we actually have to analyze more than one object, and we'll see how I apply these principles in order to figure out what's going on. Okay, so let's say we have some elaborate structure. I'm going to call it a table, and I'll hang an object from the bottom of it. So I'm going to have here a floor. Apparently my floor is not very flat. And here's my table. There's a leg and a leg and a surface of the table. And then here's my object hanging from the structure. So this could be like something hanging from a swing set, or you could have some frame set up with a hanging scale and hang your object from a hanging scale. So this red thing is the framework that holds up some beam, which I'm calling a table, and then the blue object is hanging from it. So I'm going to call this M1, and the table I'm going to call M2. So since I have two different objects, two different masses, I need to apply Newton's second law two different times. So I'm going to make one diagram for each version of the equation. So my first diagram is going to be for M1, my hanging mass. And I want to think about the forces that should exist affecting this mass. And the first one, of course, is gravity. So we put that in here. Let's go downward, Fg. And then I work my eyes around the object and I see it's not touching anything except a string. So that string is going to exert a tension force, and the string is above it, so that tension force is going to pull up. Force of tension. And that pretty much does it for M1's diagram. So now I can go over and do M2's diagram. Here is M2. And I don't want to forget to include Fg. And at this point I have a problem, because I have two different masses with two different forces of gravity, but I'm using the same symbol for both of them. Because my notation that I like to use always uses a capital letter F for force, and then the subscript is what kind of force it is. So the G stands for gravity, the T stands for tension. And I have two different gravity forces, so what I do here is I'll add another subscript to say which gravity force it is. This one's Fg2, and this one over here is Fg1. So now I need to think about what is touching the table. So the table is touching the floor, so I need to have a normal force, F sub n. And I'm just going to consolidate the whole floor force as one single normal force. We'll talk later about how we can figure out how much force is on the left leg versus the right leg, but I'm just going to call it one single force for now. And then the table is also touching that string. So we have to exert a downward Ft on M2. So at this point, we have two valid force diagrams for two different objects, and we have actually already applied Newton's third law. Newton's third law of action-reaction says that if an object is affected by a force, it returns that force in the opposite direction to the other object. So M1 is affected by a tension force pulling it upward. It's returning that force to M2 as the exact same magnitude, but in the opposite direction. So Newton's third law is already built into our analysis. And now all we have to do is maybe we'll get some numbers here. Say M1 is equal to 2 kilograms. So Fg1 is M1g. So we talked about how the force of gravity is calculated by taking our mass times 9.8 newtons per kilogram. And that comes out to 19.6 newtons. Over here, let's say M2 is 0.5 kilograms. So Fg2 is 4.9 newtons. Half of 9.8 is 4.9. So that's the first thing I can do from given information, is I can calculate those two forces of gravity. Now I can do my F equals ma analysis. So I'll say I'm doing M1 y direction. It's probably a good idea to declare what object you're analyzing and what direction you consider to be the positive direction for the purposes of that analysis. So then we look at M1's diagram and say, what forces on M1 are in the plus y direction? That's just tension. So we put that in without a minus sign. And then there are no other up forces. So then any negative forces, that would be the FG1. So that is minus FG1. And then on the other side of the equation, remember our equation is F net equals MA. On the other side of the equation, we need to think about the acceleration. And if this whole thing is stationary, the acceleration is 0. So I'm just going to put my 0 in here. So that's what tells me that Ft is equal to Fg1. And we already calculated the number, so it's 19.6 newtons. So we got some results out of that already. We know how strong the tension in that blue string is. Now we can go over to the other object and analyze M2 in the y direction. And I think, okay, I need to add up all the forces in the y direction on M2. I have the normal force is up minus the tension force is down minus Fg2 is down. And then the table's not moving, so its acceleration is also 0.
So what happens if you have like two separate, I guess, like signs? Like you would say, like, I guess the f of normal would be negative, right? Minus the t, and then you, let's say you have the f of t plus g of 2. Would that be like a?
Well, gravity is always down,
Oh, okay.
and the normal force is always away from the object.
Oh, okay.
So this normal force on the table is coming from the ground.
Oh, okay.
So that normal force points away from the ground.
Mm-hmm.
But that's a decision we make up here while we're making our diagram.
Oh, okay.
Once we go from the diagram to the equation, we just say that Fn was up, the label went off the screen, so it's positive. The Ft is down, so it's negative. The Fg2 is down, so it's negative.
Oh, okay.
So then this equation is more complicated, so maybe I want to plug numbers in at this point. So we have Fn, I don't know, minus, oh look, I know Ft, it's 19.6, minus, I know Fg2, it's 4.9, equals 0. So that's how I find out that Fn is equal to 24.5 newtons. Now, one thing that I find interesting is to ask myself, what does each force do in this scenario? So, what does the tension force do? The tension force holds up the weight of the hanging mass. It holds up the 2 kilograms, which weighs roughly 20 newtons. But what else does the tension force do? The tension force is also in here pulling the table down. So usually any given force, if it's an internal force, should accomplish 2 things. It should pull on 2 different parts of our system. And there I introduced a word that is a keyword for force analysis, the idea of an internal force. If we're analyzing a couple of objects and one of the forces acts between our objects, that's called an internal force.
So the tension.
This tension is an internal force. If the rope goes off our diagram, then it's an external force. If the other end of the rope isn't part of what we're analyzing, then it's external. And then what does the normal force do? Well, the normal force has to hold up everything. One thing that I think is interesting is M total is 2.5 kilograms. That is, if I add up the two masses, and Fg total is 2.5 times 9.8, which is 24.5 newtons. So one option we could have had at the beginning of this analysis would be to combine the table and anything hanging from or on top of the table and think of it as one compound object. We call that a system. And say, well, what's the mass of the system? 2.5 kilograms. And then calculate the force of gravity on the total system. And then say the system is held up by the normal force. So that's an option for how to analyze this situation, is to combine the parts into one compound object. Now, one of the important aspects of this example is that the normal force on the table adjusted itself to keep the table from sinking into the floor. If there was no hanging mass, then we would have just had this Fg2 and the normal force would be 4.9. But when you actually hang this mass, it puts more weight on the legs of the table, so the floor automatically pushes back harder. And that was one of the things that really struck me as unusual when I was first learning physics. I thought of tables as pretty dumb, and the idea that the table automatically readjusted the amount of its force depending on how hard I push on the table, just amazed me. So that's one of the things we have to be aware of about normal forces, is they don't have a well-defined value. They can have almost any value. So what happens if we pull upward on the table? So I'm going to have a drawing with a floor. And I'm just going to represent my table as a block with M table. And I'm going to apply an external tension force I'm going to call force of pulling. So just imagine doing this. There's something in front of you. You start pulling upward on it. If you pull hard enough, you're actually going to pick it up off the ground. That's what we want to see in our equations here. So when I do my force diagram, I should have M total. I should have force of gravity, and I should have force normal and force pulling. So then my equation is force normal plus force pulling minus M table G is equal to 0. Notice this time, instead of putting in the force of gravity as a single symbol, I decided to put it in as mass times G, because it's always mass times G. That's very common to do in our equations, so sometimes I'll do it one way, sometimes I'll do it the other way. So then we get force normal is equal to mg minus force pulling. So what that is telling me is that when I pull upward on the table, that reduces the amount of normal force. So let's do M table equals 2.5 kilograms. So M table G is equal to 24.5 newtons. And I'm creating force of pulling, so that's kind of like my independent variable. And the force normal is what the universe does in response. So, for example, if I exert 0 force pulling, I'll have 24.5 newtons worth of normal force. And if I exert 10 newtons of pulling force, I'll have 14.5 newtons of normal force. 20 would lead to 4.5. 30 would lead to minus 5.5. No, we can't do that. By the time we do that, Fn can't flip directions. By the time we do that, the normal force went to 0. When the normal force goes to 0, we have to remember that the normal force is a contact force. 0 force, 0 contact. That's when we lose contact with the surface. So then 0 is minimum F sub n and max force pulling. Now, we're allowed to pull with 30 newtons of force on this object. It's not that that's forbidden. It's just that our model doesn't allow a normal force in that case, because the normal force can't go negative. So, what happens if we do pull upwards with 30 newtons of pulling force? So then our diagram changes. We have our M total. We lost normal force, so we lose contact with the floor. And we get force of pulling. So we have force of pulling equals 30 newtons. We have mass total is equal to 2.5 kilograms. And we have F net equals MA. What do you think is going to happen? We're going to accelerate this object. It's going to go upwards. So how much acceleration is there going to be then? Did you get 2.2 meters per second squared? I left something out of this. The way I've drawn it so far, I didn't do my force diagram, and I didn't do the equation. Maybe we should do the force diagram and the equation, see what's going on here. So here's our MT. What's the first force we put on our force diagram if it exists? Gravity. Yeah. FG equals 24.5, and force pulling equals 30. So when we make our equation, it's F pulling minus FG equals MA, or 30 minus 24.5 equals 2.5A, or 5.5 equals 2.5A, which is where I got A equals 2.2. So we pull on an object with 30 newtons of force. The first thing we have to remember is that that 30 newtons of force has to fight off any other forces that exist. Then the result, sometimes called the resultant by our textbook and other people, I hate that word, but this total force is what causes the acceleration. So you pull a little bit, nothing happens. You pull a little bit more, nothing happens. And you pull a little bit more, and you lift your object. And that's what's happening here. I pulled a bit harder than gravity. My normal force vanished. And instead of having a normal force, I have upward positive acceleration. Any questions about that? Yeah?
So the force of gravity is 24.5 because of the mass times gravity?
Absolutely.
Okay.
Yes. And that is constant. No matter what we do to this thing, its force of gravity is going to be 24.5. Yeah. So let's see how we deal with diagonal forces. So let's take this thing here. There's a floor. Here's an MT. And we'll go with force of pulling is equal to 30 newtons. But at an angle of, let's not make it 30 degrees, let's make it 35 degrees. So this is the case if you were like pulling some kid on a wagon or something like that. And one of the things I'm going to say is no friction. We'll deal with friction on Tuesday, not today. So now I want to draw my force diagram for this thing. There's my MT. Actually, I'm going to put the label on the other side, MT, because I'm going to need stuff on the right side in order to label the pulling force. Okay, we have our force gravity. We have our force normal. And now we have this force pulling at an angle of 30 degrees to the horizontal. 35. Yeah, don't let me go too far with a mistake like that. So here, we're going to have to think about splitting FP into components. This is why we talked about vector components the last couple of weeks, because this diagonal force has some horizontal nature to it and it has some vertical nature to it. So we want to think about FPX and FPY. And let's start off with signs, pluses and minuses. This force is in the plus x direction and the plus y direction. So I don't need any minus signs. Each one of these is going to start with our 30 newtons. And one of them is going to be multiplied by the sine of 35 degrees. The other one's going to get multiplied by the cosine of 35 degrees. And the cosine goes with the adjacent, because SOHCAHTOA, cosine is adjacent over hypotenuse. So the adjacent for that angle is x, so x gets the cosine. And this is sine 35 degrees. So now, when I do my F net equals ma, I need to do it twice. Once for the x direction, and once for the y direction. And as I go through each of these, I need to think about what forces are affecting that direction, and then what is going to be the acceleration in that direction. So one way to do it is just to do the x equation and then do the y equation. Another way to do it is to go through my forces and say, okay, for that normal force, is it in the x or the y direction? It's in the y direction. So I'm just going to put normal force in the y equation. And then another cardinal force is gravity. It's downward. So I think, is it in the x or the y direction? I put it in the y direction, minus Fg. And then I think about that diagonal force, the pulling force. And that is the one that's part x and part y. So this is going to be plus Fpx, and this is going to be plus Fpy. And I know that I have a way of calculating Fpx and Fpy when I need it, but symbolically I've put them there. And then on the other side of the equation, what's going to happen to this object? If it's going to move horizontally. It can't go downward because there's a floor there. So let's assume that it stays on the floor. Because after all, we have a normal force there. The normal force implies it's touching the floor. So if it's touching the floor, it's not moving up or down. It's touching the floor. And then in the x direction, that's where we have the mass times acceleration. So this is 30 cosine 35 degrees, which is a number. 30 times cosine 35 is 24.6. 24.6 is equal to 2.5a. So then we can divide both sides by 2.5, both sides of this little equation, and get 9.83. Is A. So this thing is going to accelerate sideways faster than the force of gravity would do it by itself. Then let's check the y equation. We have Fn minus 24.5 plus 30 sine 35 degrees is equal to 0. So I have to rewrite it. Fn equals 24.5 minus 30 sine 35 degrees is 24.5 minus 30 times sine 35, 17.2. So Fn turns out to be 7.3 newtons. So if I pull in this thing 30 newtons at a 35-degree angle, then it'll stay on the ground. I know it stays on the ground because my normal force is positive, and that's what tells me that I'm still in contact with the ground. And not only will it stay on the ground, but it'll move sideways. So it'll move in the plus x direction with an acceleration of 9.83 meters per second squared, faster than the acceleration due to gravity. So our F equals ma equation is a vector equation, and the easiest thing to do to take care of that is to separately think about the x direction stuff and the y direction stuff. And as I went through my forces touching the object, I decided for each force, is it going to be an x direction force or a y direction force? Next one, that was a y direction force. Next one, a little bit of both. And every force is going to be in either the x equation or the y equation or a little bit of both. So let's do another example. A mass hanging from the middle of a string. So I'm going to have a wall here and another wall here. And I'm going to have my mass here. And then I'm going to have a string go across, down to there, and down to there. And I need to label some angles somewhere. So let's draw a little horizontal line here and call this theta and call that theta.
Don't the two, I guess, sides cancel each other to equal the middle portion?
Well, let's see what happens. What the heck? Oh, it's in the same text box. Let's say the walls are 4 meters apart. The string sags, let's see, 4 meters apart is like the length of this screen. The string sags 10 centimeters. And the mass is 2.5 kilograms.
The tag 10 meters, would that be like 10 centimeters from the vertex up? Yeah.
Yeah. That's 10 centimeters from the height of where it's attached. So I need to know how strong of a string do I have to have in order to hang this thing there, because I don't know, I don't want it to hit the ground. So something that we use while we're trying to figure out force components is angles. And I don't know the angle, so I need to do a little bit of a triangle first. So the first thing I want to do is think about a triangle with the wall and then half the string, and then that horizontal line. And according to my description, this is 0.1 meters. And since the walls are 4 meters apart, this is 2.0 meters. And that's my angle theta. And I chose the angle theta because I think it'll be useful to help me figure out what's going on with these ropes. So I created the angle theta, and I want to relate the angle theta to some triangle involving my given information, or involving measurable information. So that tells me that tan theta is 0.1 over 2.0. So theta is the inverse tangent of that. The inverse tangent of 0.1 over 2, which is 2.86 degrees. Okay, so that does it with my geometry analysis. Now I need to do a force analysis. So what object do I want to analyze?
Bring in the map and the block.
If I analyze M total, I'm going to find there's an FG and an FT. And this is the red string. And I'll find FT red is equal to 24.5 newtons, which is the result we had before when we had the table and the mass sitting on the floor. The normal force was 24.5 newtons. So that's actually kind of boring. The trick here is to analyze the knot, the connection in the string. And this connection is going to experience a downward 24.5 Newton force, and it'll experience a diagonal FT blue and another diagonal FT blue. Let's just put the letter B there. So now we can do F equals MA on the knot. Let's analyze the y direction. I have the minus 24.5 newtons. That's pulling down on the knot. And I could give it a name. I could call it FT red, but I'm just going to call it negative 24.5. Plus, now I need to calculate some components. So there's my reference, my horizontal. There's my theta. The theta that I calculate here and here and here is measured between my force and the horizontal. So that means the x component gets the cosine. I'm doing y components, so I use the sine function. So my tension is going to be Ft blue times the sine of 2.86 degrees. That gets one of them. The other one's going to be the same thing. So why not just multiply it by 2? And then all of that has to equal 0 because the knot is not moving. So that means that ft blue times 2 sine of 2.86 degrees is equal to 24.5. So ft blue is equal to 24.5 over 2 sine of 2.86 degrees, which gives me my tension.
Wouldn't
20.
Wouldn't your be FTB equal 12.25? If you divide that T first?
I'm just putting it together as one big formula. $245 newtons. So holding up this 24.5 Newton object requires 245 newtons worth of tension in my string. And that's because the tension force is over here busy fighting itself. Most of this tension force is horizontal. So there's a leftward tension and a rightward tension, and the leftward x component of the tension and the rightward x component of the tension are busy fighting each other. And it's only the y components that are both upward and cooperating with each other. So this 245 Newton force is busy canceling itself out mostly, which is why it has to be so strong just to hold up that object. So this can be used to our advantage sometimes. If you have a vehicle that is stuck in the sand or something, and you have something that you can tie a rope to, something strong, you can tie that rope and then push downward on the middle of the string with a gentle force. And you'll generate a large amount of tension in the string, which might be just enough to help get your vehicle unstuck a little bit. Or it might be just enough to move your vehicle a tiny little bit, and then you can lay off the string, pull in a little slack, and then step on the string again. And repeatedly pull the vehicle little by little by little with a rope that's, say, wrapped around a pylon or something. Should work. I haven't tried it. I try not to get stuck. Well, if you have another truck, then that's easier. Okay. I think what we should do next is talk about the inclined plane. Now, I don't want to do any friction today, so that's going to lead us to a bit of a slippery slope here. Yes, I really did just say that. Yes, I think I'm funny, just in case you were wondering. Now, I have a suggestion for making drawings of inclined planes. I haven't even started to draw yet. My suggestion is draw a gentle slope. Avoid 45 degrees. And you'll see why I want to avoid 45 degrees in a moment. So I'm going to draw a nice gentle slope. So there's my surface here. And I'll put in a label for the horizontal and an angle theta. We almost always label theta to be the angle from the horizontal. And then we'll put our mass up here, mt. So now I want to think about what should the force diagram for this thing look like. So here is our MT. And of course, it's going to have that straight down force of gravity. But now, when I go to say that the mass is touching the slope, and I need a normal force, I have to remember that the normal force is tilted. Not much, just a little bit, because we drew a gentle slope. So when I draw my normal force here, I'm going to draw it at a little bit of a tilt. F normal. Now, if you put an object on a slippery slope, it's going to slide downhill. And that's important to think about, that we know the result of this activity is going to be an acceleration. So off in this diagram, I'm going to draw a downhill arrow labeled A to remind myself that the acceleration in this situation is diagonal. So now I'm going to try to apply F net is equal to ma. And I'm just going to do it kind of symbolically at first. So I'm going to have force normal vector plus force gravity vector. I'm not putting a minus because the minus is hiding inside the variable here. When you have a vector variable, it includes direction inside it. And then this is going to equal mt times a. Now, if I just go and make my x and y equations like I did before, it's going to be really complicated, because if I think about the directions of these things, this is diagonal, and that is also diagonal. So I'm going to have two different forces that are going to end up with sines and cosines in the different equations, and it's going to be a big mess. This thing here is vertical. So we've developed a strategy for how to deal with this situation, where most of our vectors are diagonal. We would much prefer it like what we had on the previous page, where we had a bunch of vertical and horizontal vectors that lined up with our coordinate system. So what we're going to do here is we're going to tilt our coordinate system. So that's my y-axis. It's not the regular y-axis. Sometimes we call it the y prime axis with an apostrophe. And then perpendicular to the y-axis is the x-axis, which points up and downhill. And that's called the x prime axis. So x prime is, bless you, x prime is downhill, y prime is the normal direction. That's the simplest word I can use to describe those things. So the regular y-axis would be up. The regular x-axis would be rightward. But I've changed my coordinate system. I've just tilted the entire coordinate system. So what that does for me is when I go to put my normal force into my equations, my normal force is in the y prime direction. That's just F sub n in the y direction. Let's skip gravity for a second. Leave a half-inch space here. Equals. My acceleration is downhill. My acceleration is in the x direction. So that means that I can put MTA here and 0 there. Because my object is going to be on the surface. It's not going to move in the normal force direction. It's also not going to move into the surface. And I skipped a vector. I skipped the gravity vector. The gravity vector is not aligned with my coordinate system. So my gravity vector is going to go both places. Let's call it FGX and FGY prime. Now those are symbolic ways of describing the gravity force's components, and they're hiding some minus signs. So let's figure out the gravity force's components. In order to figure out the gravity force's components, I need to find my angle theta. That angle theta over here on this original diagram, the angle of the slope, it exists in this other diagram somewhere. And this is where it comes in really handy that I drew my slope as a very gentle slope, because theta is just a little sliver of an angle. And we can see in the force diagram exactly where that little sliver of an angle is. That little sliver of an angle is right here. That's theta. So then, which axis is adjacent to theta?
Or the what?
This y-axis is adjacent to theta. Gravity is going to be my hypotenuse. And then my hypotenuse is up and down. And one leg is adjacent, that's the y-axis. And then the x-axis is perpendicular, is opposite to theta. So FGX prime and FGY prime, this is going to be, let's just call it mg cosine theta. And this is going to be mg sine theta. Now when I use triangle trig to figure out which thing gets the sine and which thing gets the cosine, I have to be very conscientious about my sines SIGNS. I have to be careful about the sine SIN and my plus and minus. So I need to think about whether these things are positive or negative. So does gravity point more x prime downhill or against x prime uphill? Gravity points more x prime downhill. So this one's plus. And does gravity point more with the normal force or against the normal force? Against, so that one's negative. So now my equations look like this. M total G sine theta equals M total A. That's my x prime equation. And my normal y prime equation is force normal minus M total G cos theta. And that's 0. So our gravity force is split into components. Even though gravity is a vertical force in the minus y direction, the real minus y direction, in our tilted coordinate system, gravity is in the partly x prime direction. That's the downhill component. And the normal force component causes the normal force. So gravity on me causes the normal force on my feet. Gravity down makes the normal force act up. This gravity down makes the T, N, N, N. Makes the normal force exist. So let's put some numbers on it before I send you away for the weekend. MT is 2.5 kilograms. Theta equals gentle angle, 10 degrees. So A is G sine theta. Notice in the x equation, the mass cancels out on both sides of the equation. So that is 9.8 sine 10 degrees. 9.8 times sine of 10. Oops. .7 meters per second squared. And the normal force is m total g cosine theta, 24.5. We've multiplied 2.5 times 9.8 a few times throughout today. It's 24.5 all day. But now we're multiplying it by cosine 10 degrees. So 24.5 times cosine 10 equals 24.1 newtons. So as it turns out, the normal force on an incline is a little bit reduced. Depending on how big the angle is, it could be a lot reduced. And part of gravity is used to accelerate this thing, but not with 9.8 meters per second squared of acceleration, because the other part of gravity is causing the normal force. But not the full normal force. If you had a level surface, it's a reduced normal force. Today's examples are all essential, absolutely essential. I will ask conceptual questions about these examples on test 2, which is in like 6 weeks or something. It's in forever. But please make sure to remember that lecture 12 was the most important one in understanding forces. All right. You guys go have a good weekend.
Is the box given to everyone? It's right around the corner. Look how fast we're right now.